Good day, everyone. My name is Craig Mahlasi. I'm a PhD candidate in the Center for Statistics in Ecology, the Environment and Conservation at the University of Cape Town. This presentation will look at the first two chapters of my project titled Near Real-Time Change Detection in Subtropical Thickets. The project supervisors are Dr. Glenn Moncrief, Dr. Vernon Visser, Dr. Jasper Slingsby, and Professor Rez Altwig. We know that thickets have been and remain in peril of degradation. Stickler and Shackleton noted that approximately 63% of thickets were classified as severely degraded by the year 2015. Alexandria is an example of such extensive and an ongoing clearing of thickets, much of which is caused by agricultural land expansion. While several works have been successful in identifying and documenting clearing events, most of these studies have, however, focused on temporally static assessments of clearings. For example, a snapshot comparison between two dates. While these maps may carry a wealth of information, they do suffer from the inherent inefficiencies of snapshot comparisons. We know that the time series analysis are a good way of dealing with some of these inefficiencies. The aim of the study is to detect clearing of subtropical thickets in near real time using remote sensing or Earth observation data. The objective of the first chapter is to generate a transformation or change map of Alexandria between 2016 and 2019. The second chapter looks at building workflows for continuous change detection in Alexandria. I'll give you a brief background of Alexandria. Alexandria is a small town located about 100 kilometers northeast of Gqeberha. The main economic activity here is citrus, particularly pineapple farming. There's also a bit of chicory farming. Here is a schematic of the two chapters. What's important to note in this schematic is the link between the two chapters, meaning that before I could do any near real-time change detection analysis, I had to perform a recent period. By recent period, I mean 2016 through to 2019 transformation analysis. The reason the reason for focusing on 2016 through to 2019 is the presence of a detailed data set that documents a transformation in Alexandria. The dataset is produced and maintained by the Rhodes Restoration Research Group. Another thing to note in this schematic is that the second chapter is, by and large, a comparison between two continuous change detection frameworks, namely the continuous change detection and classification framework and the temporal convolution neural networks framework. For the sake of this presentation, I will only focus on the best performing framework. To produce a transformation map of the study area, a single image from the years 2016, 2017, 2018, and 2019 were combined to create an image stack comprising of four Sentinel-2 images. A reference dataset was created by adapting the Rhodes Restoration Research Group dataset. The adaptation resulted in the following classes: forest, stable forest, forest gain, forest loss, stable thicket, thicket loss, thicket gain, and stable non-forest or thicket. A random forest classification was then trained by using these two datasets. Here is a lightweight application put together using Google Earth Engine. We see the final classification and a zoomed in example of thicket loss. On the left panel is a graph showing the area extent of each class in square kilometers. Following the classification, the pixels that were classified as lost thicket were extracted from the classification. This resulted in 186 individual instances of lost thicket. The distribution of these instances can be seen in the map. Dates were then allocated to the clearing events. The date when thicket was last confirmed to be present was recorded, as well as the date where an entire instance was confirmed to have been cleared was recorded. This exercise was done using daily planet scope imagery from Planet. The next task was to perform continuous change detection in Alexandria. This section looks at one of the frameworks used to perform the continuous change detection. The other is called the CCDC, or Continuous Change Detection and Classification. The analysis in this section make heavy use of Google resources, including Google Earth Engine, the Google Cloud Platform, Google Collaboratory, and TensorFlow. Most of these resources are available free of charge, and from a long-term monitoring perspective, this presents many possibilities. A 2016 to 2019 time series of Sentinel-2 reflectance data, as well as spectral indices, including the normalized difference vegetation index, the normalized difference water index, and the enhanced vegetation index, were used to train, validate, and test the model. The time series comprised of 360 images in total. The bar chart here shows the number of images per year. The difference in the number of images a year is attributed to the cloud filtering that was done. Images containing 60% and greater cloud coverage were excluded from the time series. Here we also see a map of the reference data used. There were a total of 1,879 dated thicket clearing examples and 1,927 stable thicket examples. The time series was subsampled into windows of 120 observations or images. Here's an example of one of the windows. I used 12 and not 120 images in this slide for the sake of not congesting the slide, but bear in mind that each window contained 120 observations. We see that by the 7th observation, thickets were confirmed to be present, and between the 8th and the 9th, some disturbance, there's signs of disturbance, though not completely sure of what's happening in the area. But then by the 10th observation, the clearing event is confirmed. Temporal convolutional neural networks, or TempCNNs, were implemented in Google Earth Engine to perform the change classification. The temporal convolutional neural network architecture comprises of 3 convolutional layers with filters of the same size. The convolutional layers are applied consecutively, followed by one dense layer, and finally one softmax layer. The softmax layer provides the predicting class distribution. Here we see how the model performed. The table shows the evaluation performed on the testing dataset. We can say that TempCNNs do well in detecting changes in thicket ecosystems, with the recall of 93% and a precision score of 91% when detecting clearing events in thicket. We can then use the trained model to make prediction on new dates by adding any newly collected image to the time series of the previous 119 images. So for every 5th day, we'll have a new image coming in, added to the previous 119 images, and change detection being done on that 120 images. Here in this example, we see how the model was able to detect stable thicket and cleared thicket as of the 30th of October 2021. The results look really promising, but there's still a fair amount of work that needs to be done. And one of those is that I'm currently experimenting with shorter observation lengths, meaning I would like to reduce the observation length from 120 to something shorter. I'm also exploring ways to account for rainfall, for the rainfall or moisture gradient in the study area. that may be having an effect on the prediction accuracy, especially in the northern regions of Alexandria or the study area. Finally, I'll wrap it all up with an interactive app that will be made available. Here is a zoomed in example of a clearing event that the TempCNN was able to detect. The image on the left is an image acquired at the beginning of the time series. The image on the extreme right is an image acquired on the 30th of October 2021. And in the middle, we have an image of the probability distribution. The white areas are where thicket is said to be stable and not cleared on that date. And in the darker shades of blue are areas with a high probability of clearing. Before I close this talk off, I'd like to thank these organizations that have played some or other role along the journey of this project. I've attached my email address should anyone have any questions or suggestions. Once again, thank you and bye.